So last week we left, or not last week, earlier this week, we left off on different probe types, and I was talking about probe configurations. Just a quick reminder on those. You'll also hear them referred to as coils, but know that a probe can have more than one coil in it in some cases. There's two kind of configurations we're going to look at. One is the physical structure of the probe. The other one is the coils and what they're intended for inside of the probe. And I talked about this style here, the spring-loaded. This is where I left off. So here they could have a single or multiple coils mounted in the spring-loaded kind of carrier in the center that's got the arrows pointing to it. And then the remainder of the probe body shown here is used to help stabilize. And this works great on a flat surface, but it's limited when we start talking about curved surfaces. So there's some other standard shapes that work for different object shapes or different material shapes. And those are things like pencil probes, bobbin probes, and the like that are designed for kind of general purpose on certain styles or certain shapes of objects. There's also custom shaped probes for specific application, and wheel bead seat profiles are one. Another one is they make probes that fit into like the fir tree areas on fan blades or compressor blades or turbine blades. You know, those high stress kind of V-shaped areas that have a lot of stress risers and could potentially be prone to cracking. The spring-loaded probes I mentioned help keep the coil on the surface, reduce the amount of wobble, and reduce false indication when you're working with some kind of a flat object. And then other configurations, now looking at the inside, we can have more than one or multiple coils. We can also have things like shielding, loading, and stuff like that, where we either put different materials around the outside of the probe to limit interaction with things around the probe, or loading the coil with things in the center of the windings, typically ferrous materials in the center of the windings to concentrate magnetic fields, to help concentrate them directly under the probe, or for especially if we're trying to get a deeper depth of penetration. And so the other part is the coils themselves can be different sizes. So we talked about frequency is probably our biggest variable that we have control over. Certain styles or shapes of coils lend themselves better to different frequencies. So smaller coils tend to be operated at higher frequencies. They have a natural resonant frequency that works better with higher frequencies. But they don't produce as much depth of penetration. So they're really good for finding those small surface flaws, because they also have high sensitivity. It also gives us areas, the smaller the probe, the easier it is to fit into irregularly shaped surfaces. You know, if we have a curved surface and we try to put a wide flat probe in there, it's going to bridge that curvature. It's not going to sit flat. But if we have a very small diameter probe, we can run it through some kind of a curved area in order to scan it. So we have that kind of thing. They also reduce something called edge effect, and that is, as our probe gets near the edge of a component, it'll change that inductive reactance of the probe, because we've got less material, less metal, underneath the face of the coil as we start to get near the edge, right? So if we have a piece of material like this, and we put our probe on the surface, the magnetic field isn't going to go just straight down. It's going to spread a little bit, right? So as we move that probe over towards the side, a portion of that field now, those flux lines, are going to send out. So we're not going to have as much material generating those eddy currents underneath the face of the probe. And so it's going to change. You're going to get a different inductive reactance here in the middle than you will when you get near the edge. But the smaller the diameter of the probe, the less that this field spreads out. It's more focused underneath the probe. And so it can reduce that. The downside, though, is slow coverage. You can imagine if you have a probe that's the size of the tip of my pen, and I want to do a big area, it's going to take me a long time to scan the whole thing. whereas something that's larger might be able to scan a larger area in a shorter period of time. So larger diameter coils are the opposite of that in just about every way. So they're operated typically at lower frequencies, which gives us a greater depth of penetration, which means they have lower sensitivity to small flaws, but they're good for subsurface flaws. So what's some examples of subsurface flaws we might use these to find? What have I mentioned earlier? Backside corrosion on sheet metal is probably the most common one in aviation. What other type of things? Let's hold delamination for ultrasound, because we can't really do that unless you have like a metal composite. I guess if you had some kind of a metallic composite, you could use eddy current. But if it was like, and one of the airplanes I worked on was metal composite. The Saab 340, the sheet metal was actually layers of sheet metal bonded together. So in theory, we didn't use eddy current for that. We used ultrasound, but in theory, I could see where eddy current could be used for something like that, because a slight separation is going to change how much, what kind of flux buildup and what kind of eddy current buildup we'll get in there. So I could see it in a metal composite. Anything else that might be subsurface? So one area that's used for is, it's also for fan blades, but if you have batches of material where there's a potential for a manufacturing flaw, and especially if it's realized after those items are in service, there have been cases where things like fan blades, they've realized there were potential for inclusions in the metal. Inclusions are things that shouldn't be in there that have gotten mixed in. And if they're down inside the part, they could potentially create a weak spot internal in the structure. And so if you have an area where there might be an inclusion, you probably don't know much about forging, but when you forge parts, you hit them with a lot of force and they flow. The metal's supposed to flow into areas. The metal can actually do what's called a lap, an overlap, where it folds over itself. It's not supposed to. You're trying to get it to expand out evenly. But if it laps over itself, it can actually fuse back together and create like a pocket inside of it. So you could potentially use these to find parts where they realize after they've been forged that there was like a lapping issue, which is a flaw in the die design. The metal doesn't flow correctly, but sometimes they don't realize that till after the parts are in service. Now you got to figure out which parts have and which don't, right? You don't want to scrap every part that has a potential, because if you have good parts, that's wasting material. So they can be used for that as well. And then being a larger diameter coil, a larger probe, we can cover a larger area in a given amount of time. So you're going to make the inspection process go faster. Here are some of those profile probes that I talked about. So here's one where the probe in this case is embedded in typically a plastic piece that's designed to fit the shape. In this case, it's like a turbine disc or a compressor disc. It's a bulb style blade root where the blades would key in there. We want to make sure, for instance, that we're not getting cracks, between these tabs that form the different bulb cavities. Below that, we show something called an array probe. This is the connector. This is the actual probe itself. And so in this case, it's multiple coils. They have like a whole, like rows of coils there. And so it allows us to scan a large area quickly. It also can allow us to produce more of an image of what we're seeing. So they can actually create 2D and 3D images rather than just having some kind of a little inductive reactance trace on the screen. So when you know how wide the different probes are, you actually put a little device on here, a little wheel that as you move it across your surface, it measures how far you've moved it, so it can give you a 2D, or based on how deep the different flaws are, showing a 3D map or view of what your flaws look like. Bolt holes are often inspected, so we have a bolt hole probe here. So this is just the holder for it. This is to hold it against the surface. The actual probe is just typically one little coil in this bulb. The bulb on the end is designed to push out against the inside of a bolt hole. And there's a coil on one side. We'll use these. We have these in the lab, and you can actually see where the coil sits in here. and you put it down inside of a hole and then rotate it. The one that's shown in the picture here, ours, you put them in the hole and you rotate it manually. The one shown in the picture here, this is a little motor that'll actually rotate it automatically. It makes it less likely that you'll wobble it and cause false indication. The other thing it can do is it can track how far it's been turned over a given time, so it can kind of give you positions more than just like turning the probe until you see some kind of an indication. And then this below is an encircling probe. So we take a coil, and rather than putting it next to something, we actually put our part through the center of it. And any changes in the part geometry or flaws in the part or anything like that are going to change the inductive reactance of this encircling coil. And so we can run our part through the middle of it. Okay. Those are a couple other configurations. So you see there's a lot. These are general purpose. You know, they're not like this probe here, this profile probe that's a very specific purpose. This is a general purpose, but they're more specialized than just a flat single probe or coil that we move across the surface. Right? Bobbin probes are kind of the opposite of the encircling probes. So we put coils, and it can be one or more. In fact, this shows combinations of not just more than one coil, but coils in different directions. So these are coils wound around the outside of the probe. Here we have coil discs, and so they're actually going to produce eddy current fields that are oriented in two different directions. So just like we did with mag particles, sometimes the field orientation can make a difference in finding flaws. Or possibly one set of these coils is designed to measure the inside surface of our material, and the other set of coils is designed to look at the outside surface of our material. Where would something like that potentially be used? What do you think? I'm going to give you a hint. Think outside of aviation. What's tube shaped and runs in areas where you can't look at the inside or the outside of it? Pipes, underground pipes. They run these things through things like gas lines, oil pipelines. And they can run through and they inspect the inside surface to make sure there isn't any corrosion or any crack on the inside surface. They also have a second set of coils that are penetrating to check the outside surface that's covered with dirt to make sure it's not corroding in from the outside. So these are small ones shown here, but they have big ones they're called pigs, that are the diameter of these big 12, 14, 20-inch oil and gas pipelines. And they just send them through. Okay. And then pencil probes at the bottom, the four on the left here, have one tiny little coil typically at the tip. They fit into tight areas. They fit well in curved areas and that kind of thing. And they are good for, you know, odd geometry parts. You can see they come in different shape, whether it's a straight probe, a 90-degree probe, or a bent probe. This one right here is a precision. So these ones on the left, the three on the left, you tend to hold them further up near the top. That's your grip. This one right here, that's coated all the way down to the very fine tip, is designed to hold like a pen, where you can manipulate it very, very precisely across your part. Okay. So, and then again, they can form these, they can build these in any shape, combination of shapes, combination of coils, combination of sensors that you would want. So there's companies that make custom probes, and they'll build them for a specific wheel. They'll build them for a specific fan disc. They'll build them for a specific landing gear component, a specific trunnion bearing, you know, to check those different areas.